I finished the second order system, and we had the different inputs for underdamped, critically damped, overdamped system in the previous classes. And before going to the body plot or frequency response of the second order system, I wanted to teach you what the dominant poles of the systems. So it was the example that I don't remember it because I'm teaching from my mind always, but it was like this example: a fourth order system. It doesn't matter. So I have a spring and damper here, a mass that I'm pretty sure you're expert of this from my vibration class from the previous semester. So this is M1, M2, K1, K2, K3, and C here, one damper. And I told you I'm not driving that because it's not vibration class, this is control. But the whole equation is like this. If you apply U1 actuator here and the U2, and here is X1 and here is the X2, right? So you have 2 degree of freedom system. If you remember, I told you, now you have to know it, because you have 2 independent motion, X1 and X2. And it was, I'm just writing here again based on my experience. I'm not driving because I already taught this in the vibration class, these kind of problems. X1 minus K2 X2 plus C X dot 1 equals to U1, and the M2 X double dot 2 plus K2 plus K3 X2 minus K2 X1 equals to U2. That's right. And the assumption is that because we are going to frequency domain, obviously always we have to have initial conditions. X1 at time 0 equals to X2 at time 0 for the Laplace transform, equals to X dot 1 at time 0 equals to X dot 2 at time 0. All of them, they are 0. Being said, because we want to find about the dominant poles, applying the Laplace, and I thought the Laplace of the second time derivative gonna give you S squared, Laplace of first time derivative gonna give you S, and go on. So you're gonna have this M1 S2 X1, obviously S, I'm dropping S for simplicity, plus K1 plus K2. What I want to find? I want to find say sorry, I want to find sometimes this is ridiculous. Okay, I want to find what's happening again today. Okay, X2 over U2, this transfer function. And now change the color. X1 obviously minus K2 X2 plus CS, because X dot 1. X1 is U1. From the second line is M2 S squared X2 plus K2 plus K3 X2 minus K2 X1 equals to U2. For simplicity and for teaching purposes, let me tell you that only I have one control input in the system, and I'm saying for simplicity, for now U1 is 0. Sorry, U2 is 0. Actually, U1 is 0. Okay, U1 is 0, so this is 0 for simplicity. Only I have this input to the system. Okay, only have this. Okay, good. I want to find X2 over U2. But here you see you have an X1 here, so I have to find X1 from this relation. So it's very easy. And for simplicity, because after going here, assuming, because I'm going to go to MATLAB eventually, M1 is equal to M2 is 1 kilogram. I say K1 is 10 Newton per meter. K2 is 3 Newton per meter. And K3 is 1 Newton per meter. And C damping is 1. Being said, I'm gonna write this here. These equations becomes like this. See from here, x1, x1, x1. So I'm gonna factor out x1 is s square k1 plus k2, 13 plus 13. So let me put this. C is 1 gonna be s plus 13. This is 13 minus k2 is 3. 3x2 is equal to 0. From here you get that x1 is 3x2 divided by s squared plus s plus 13. What I'm gonna do, I'm gonna put this here. Here we go. Okay, got it, everybody? Good. I'm just double checking because I have no notes. I want to make sure that I'm doing everything right. Okay, so now putting here. So again, factoring out x2, second line, is s squared. K2 plus K3 is 4. So you have 4 here. And sorry. No. Here we go. Okay, S2 plus K2 plus K3 is 4. Plus 4. This is X2 minus K2 and X1. So K2 is 3. In X1, 9 X2 divided by S squared plus S plus 18 is equal to U2. Here we go. We got it? 3 by 3, 9. This is X1, guys. I wrote mistakenly. Sorry, guys. K2 is 3, X1. So 3 by 3, 9. Okay. Can I go to the next page? So, changing the color of that, I'm factoring out x2. Here gonna be s squared plus s plus 18. And now this multiplied by s squared plus 4 in s squared plus s plus 18. This is 18, that's right, hopefully. Oh, 13, why I write 18? Guys, please correct me. Oh, because of this, it's written as 3. This is 3. 3. Okay, 3. What I say? What's wrong with this? Okay, good. I want to make sure that everything is correct. Yeah, 3, 3. And K2 plus K3 is 4, and this is 3. Yeah. Okay. Minus what? Minus 9. Minus 9. Minus 9. Here we go. This is equal to, from here, this is equal to U2. U2. So if I simplify this, for God's sake, this term, you're gonna have x2 s4 plus 1 by 1 s cube plus 13s square plus 4s square plus 4s plus 13 by 4. How much is that, guys? 13 by 4. 52 minus 9 divided by s square plus s plus 13 is equal to u2. So if you simplify everything, you get this transfer function. x2 over u2 is, this goes to the numerator. Oh, now you have two zeros of the system, guys, because you have second order systems. This is gonna give you, let me change the color. This is gonna give you two zeros, z1 and z2. We're gonna calculate that. And later in the root locus, I'm gonna teach you that the system dynamics moves from the poles to the zeros. So you have S4 here, 1 plus S cube, 17 plus 17 S square, plus 4S, plus what? Plus 43. And this is going to give you how many poles of the system you're going to have, guys? How many poles? How many poles? 4. This is high school. That's right. You're going to have 4 poles. P1, P2, P3, P4. Let me go back to, let me first double check everything because I want to make sure everything is right, okay? X says, okay, 1 plus K2 is 13, hopefully is right, plus 1 C minus K2, 3 is just, it's going to 3x2. No, this is x2, actually. Yeah, this is x2, guys. Why I wrote like that? This is x2. See here from your first line. ZU1 is 0, so this is 3x2, right? And x1, now replace here, this is correct. Minus 9, K2, x1, x2 is, and 13, and then putting here, S4, S cube plus 3S plus 4S squared plus 4S plus 52. Okay, good. So now going to the MATLAB, I want to find zeros and, first of all, poles of the system. And you know how to do it, that's right? Sims X. I'm going to say poles of the system equals to solve x4 plus, can you read the denominator for me? x4 plus x cube plus, how much is that? 17 x squared plus 4s plus 43. And obviously I'm gonna say eval to make you meaningful things. What is s? Oh my god. X. Z? What is z? Undefined function variable z? Sims X. $43. Do you see any z here? Okay. Eval P. Oh my God. Okay, here we go. Double command because I have voice. Okay, you see that we have four what? Four two pair of complex conjugate poles. Okay, and the real part is this. See, please write it down and let me know, please. Okay, please write it down. Let me know. Did you, everybody? Yeah. Okay. Just keep these digits. Okay, not more than that. Even here, 1.7, 3.6. Okay, 1.04 minus point. Okay, you got it. Okay. So now, can I go and write it in the notes? Yeah. Okay. So P1 is how much? Minus 0.04 plus how much? Okay, in I, this kind of minus 0.04 minus 1.76 I, P3 is minus 1.4, how much? Plus, okay, that's enough for me, because I want to work with the real part. 4.6 minus 3.7 I. Okay, now I'm gonna plot this in the complex plane, guys. In complex plane, imaginary and the real. Okay, this is say 1, 2. This is 1, 1. Okay, so the first first pair of complex conjugate poles, if I want to plot it here, it's gonna be like this, guys. 0.04. All of them. You see that the real part in the left-hand side means your system is what? Stable, right? The two mass in the spring and damper, they're stable. Obviously it is. If you pass the vibration with me, you know that. But very close to the origin. So suppose here's 1.76, it's gonna be here. You see the first poles of the system? Very close, huh? Here the real part is my. But the second pair, as you see here, guys, real part is almost 10 times of this first part. Almost 10 times, huh? Let's see here. For example, because this is minus plus 3, I'm just plotting here, guys. Okay, here say, okay. So its real part here is 10x almost, 10x, 10 times. Real part of the poles. You're gonna tell me, okay, what's your point payment? First, let me open a new PowerPoint because the previous one screwed. Okay. Oh. Okay. Guys, x2 over u, if you want to finally decompose and then put Laplace transform, it's going to be written as this. Look at here, s minus p1, because you have fourth order system. You remember that you were doing for the second order system? Yes, everybody? To go to the Laplace transform for the time solution of that. Finally, it's going to be this. That's right. Yes, everybody? This is equal to, let me show you. Can you read the original x2 over u for me? S squared in the denominator plus S plus 13, right? Divided by what? Now S minus P1, no, I don't need that. S minus P2, S minus P3. It always we were doing like this, remember? To decompose this. Yeah, exactly. So while we found the poles, so we have to write this to go to the time, right? With the input of the U2. When you apply, guys, what I'm telling the dominant poles, when you apply Laplace inverse to that, to go to the time domain, okay, and assuming that the U2 is 1, means impulse. U2 of x means impulse, which transpose was, I'm sorry, Laplace was 1. So you say that the x2 always was like this, x2 of t. A, E, okay, P1t plus B. I don't care what is A, B, C, D based on this term, okay? I'm just taking your attention to this point. Plus C, E, P3t plus D, E, P4t. Okay, guys. A, E, P1 is minus 0.04 plus, how much was that? Tell me, plus 1.7, that's right, in T plus B, E minus 0.4 minus, I'm sorry, this is I, 7 I in T plus C minus 0.4 now, 10 times of that, plus 3, how much? 3.7, like that? Yeah, I don't care about this number. T plus D minus 0.4 minus 3.7 I in T. You're gonna tell me, Payman, are you stupid? Yes, I am. Okay, why? Guys, from high school, you know that. This term, as I told you, the Euler formula gives you sine and cosine solution, that's right. But this term, I'm writing here, look at here, AE minus 0.04 T. And here you're gonna have, I'm writing here, sine, cosine, this is abbreviation, plus B E minus 0.04 T, again, another sine, cosine, based on the Euler. We have done this previously. C minus, sorry guys, C E minus 0.4 T, another sine, cosine terms, plus D E minus 0.4 sine, cosine. Okay, guys, I taught you a million times. What's the name of this term, for God's sake? Name of this term in mathematics? Yes, decaying term means vanishes, that's right, vanishes. Now you tell me, forget about the control, dominant poles and this kind of things. Which of these term vanishes fast? Which of these two vanishes fast? This, exactly, because this is 0.4, and if it's gonna vanish like this, look at here, in comparison. It's gonna vanish like this, because this coefficient is very slow, small. So you need big time to vanish this. But this term, 0.4 minus 0.4, if you want to plot it, it's going to be like this. I'm sorry. Just a comparison, huh? See? Here we go. It vanishes. So it means, physically speaking, the effect of this term is negligible in system dynamics. It vanishes very fast in system dynamics compared to these terms. See? That's why these two poles, P1 and P2 for these systems, are called what? You tell me. What's the topic of today? What's the topic of today? Huh? Dominant poles. These are dominant poles. Dominant poles. Okay? So generally speaking, for any dynamical system, for any order system, 10, 20, 30, 100, whatever it is, if, this is definition, a real part of poles are at least 5 times of others, that pole vanishes fast, and the remaining are dominant poles. And I showed you by high school mathematics. See, this is 10 times, not even 5 times, 10 times of them. You got it, everybody? Real part of the poles. Let me go to the previous. Oh. Where is that? Okay, I don't care. Yeah. So the real part of the poles are 10 times of here. So this gonna vanish very fast. So the effect of these poles, bye-bye, is negligible on the system dynamics. You got it, everybody? Yes. So suppose that you have a 6-order system. Let me go to the MATLAB. And it's going to help us in designing PID controller. Suppose that you have CLC Sims X S6 plus X 5 plus, I don't know, 2X 4 plus X cube plus 10 plus 6 plus 100. 6-order system means that how many poles we have? How many poles we have? Come on, 6-order. 6. Here we go. 6. Okay, guys, look at here. You have 1 pair of complex conjugate, 2 pair of complex conjugate, 3 pair of complex conjugate. First of all, your system is stable or unstable? Look at here. Real part is positive, is in the right-hand side. Your system is unstable. Okay, good. And but between two stables, okay, the effect of these for these two gonna be when because this real part is almost 20 times of this. See what I'm saying? So your system dynamics is gonna oscillate between the first two and the last two. Obviously, last is let me give you an example that is. Oh, what the hell is that? This is no. sorry, that was mistake here. See x5. Now I fix this. X5, 2x4, x3, x2. Here we go. Now I have the same problem, guys. Say 15 and 5x. Now 20. Still the same problem. 100. 200. Okay, I cannot fix it. Okay, but let's stick to this. So see, where's that? Oh, here. Where was that? Yeah, here we go. We were talking about this. See, this is almost 20 times of this. Even here, see, this is 5 times of this. So this gonna vanish too fast, the first two one. So even your system is not stable, you have to talk about these poles to fix it in PID control. Okay, you got it?
Yes.
And being said, if I want that you go, okay, let me go back here. Guys, for the Simulink, go and try this, see what the system behavior is. Obviously, you know it, but first of all, this u over x, this xt over, this is open loop transfer function, guys. This is open loop transfer function, because this is from actuator. Okay, suppose that you want to keep input to the system, desirable input to the system, that you want to keep the mass to a 0.1 meter per step function. So this is your g that we got here, was x2 over u2. Okay, you have it. And this is y output of the system. Go and simulate in Simulink for yourself. And this is your this. So it was like this: s squared plus s plus 13. Can you read for me? S4 plus s cubed plus what? 17? 13? What was that?
Also,
17 s squared. Here we go. Okay. But you have two zeros also here, okay? I'm gonna talk about this when we go to the root locus of the system. Because this coming from the actuator, force coming from the actuator controller. You have to understand physically what's the open loop, what's the closed loop. Okay? This is G. So now let's go to what? To body plot of second and then nth order system, fourth, 10th order system to complete the body plot as fifth input to the system. Input is omega square sine or cosine, because we did the step impulse ramp input previously. I told you if you want to plot let me go to the next page. The body plot for that, you have to plot 20 log of omega n square. Remember that the y over x was second order system we define as omega n square in s square plus 2 zeta omega ns plus omega n square, and its value. So what you have to do, I told you, you have to replace s with j omega as we defined. So if you do that, omega n square, what is 2 omega n square, is gonna be s square gonna be minus omega square, because j is what, how much? Root square of minus 1 plus 2 zeta omega n in j omega plus omega n square. This gives you y over x equals to omega n square. Now you have to write like this: omega n square minus omega square, real part, plus you have an imaginary part, zeta omega n j. Being said, I told you previously that this is this, okay? So we, for the body, for the first order we did was this y over x. And I told you if you have a complex number as a for refreshing is a plus bj over c plus dj, it's gonna be a square plus b square divided by c square plus d square. Exactly, I'm gonna do that here. So it's gonna be amplitude for the body plot that you know in the MATLAB also, 20 log of omega n square, because is that is, and root square of omega n square minus omega square plus 2 zeta omega n omega square. Yeah, we have to plot this. We have to plot this by changing omega from 0 to infinity, excitation frequency. And I assume I'm gonna plot only for the underdamped system, but when I go to MATLAB, I'm gonna teach you the eclectic overdamped system. Case A for the underdamped system. The guys that you had a vibration class with me, you had seen a different version of this in chapter 7, but this is control class. In vibration, we didn't have body plot. Sorry, underdamped system. I'm getting older. This is smaller than 1. Okay. So I'm gonna say case A, if omega is very smaller than 1. If that it is, so, and this is zeta is smaller than 1, so you're gonna, this is very smaller than 1, so you're gonna say bye-bye to this. Is very smaller than 1, you can say omega is very, very smaller than omega n. Huh? So I'm gonna say bye-bye to this also. So your A becomes 20 log of omega n square, and this is, you have a square here, guys, sorry for that, over omega n square, 0. Let me go back to the plot. Then I'm gonna move everything to MATLAB. Omega, and this is A. So for low frequency, everything is 0. Let me, as I plot it here, for low frequency, everything is 0. Here we go. Now case 2. If I say omega is equal to omega n, if that the case is, it's gonna be 0, everybody, huh? And your A gonna be 20 log of omega n square over 2 zeta omega n square. because omega is omega n square square, and that, here we go. So this omega with the omega n goes away, so you're gonna have 20 log of 1 over zeta. But here's the point from high school, not from even university level. I said, let me change the color. Zeta is underdamped, it's smaller than 1. So this ratio gonna be greater than 1, that's right. Log of any number greater than 1 gonna be positive. So gonna be some, say, I don't know, give me a number. For example, let me do my calculator. I say, for example, zeta is 0.1. Huh? Very underdamped system. Let me do that for you. Point 1. Oh, sorry. Log of 0.1. What the hell is this? Log of 0.1. Oh, log of 10. I'm sorry. Not 1. Gonna be 1. So here gonna be 20. Actually, this is too much because I'm gonna plug it 0.5. Log of 2. Gonna be, here we go. This is 0.5, gonna be log of 2, here we go, multiplied by 20. Gonna be plus 6.02. Interesting, in the first order system, at the resonance frequency means omega resonance frequency, when the natural frequency becomes equal to excitation frequency. In the first order system we had here going down here we have such a peak, guys, going up. Okay, and now third case, if omega is much greater than 1, so A is 20 log of, again, omega n squared. I'm writing here again, omega minus omega n squared minus omega, what is that? Minus omega squared plus 2 zeta omega n squared. So if that the case is much greater than 1, that's right. So if you put some num, obviously this, guys, this is gonna be much greater than the numerator. Means this is gonna be a negative number. This is gonna be a negative number. See what I'm saying? For example, if omega is much greater than the omega n, say zeta is 0.5, and I say omega is 10 omega n, much greater than 1. So you're gonna say 100 omega n plus c is a great number, gonna be negative b. So it's gonna come down. Here we go, like this. Now if I increase the damping, eventually you're gonna see this, and this is maximum peak, as you saw in the second order system for the frequency response. And what does it mean, guys, physically? It means the output at this resonance frequency is greater than input. This is very dangerous, guys. When you have harmonic input, your output amplitude is even higher than your input. Okay, for example, you want to have x of t desirable as 60, for example, mile per hour, whatever. But for the, this is not a good example for that. But again, your y gonna be 75 in the periodic, in the harmonic input. This is very dangerous, guys. You have to fix it. You have to put a limit here. If you increase the damping ratio, so you're gonna eventually move toward critically damp, and the critically damp gonna be like first order system, and eventually overdamp system. In the critically damp overdamp, you don't have such peak. You got it? And let me plot it in MATLAB for you. Assuming omega 1 is 1, and the omega, I have to change it from omega is 5, omega from 5 to 0.1 to 20. Zeta, I'm going to change it from underdamped to overdamped system. Let me do that in MATLAB for you guys. And we're going to see the second order body plot. I'm going to share this with you. CLC, clear all, close all. I'm going to say omega n is 5 radian per second. Omega there we go. So num is close the transfer function is 0, 0 omega n square, and then for zeta from 0.1 to 0.3 to overdamp system. So then gonna be 1 to zeta omega n and omega n square. And figure one body num and grid and 2 zeta omega n omega n. I'm gonna say second order body in ME530. Here we go. You see that, guys? Oh, I forgot. Sorry, guys. I forgot to put hold on. There we go. Here we go. You got it? This is very underdamped. Eventually increase the damping and going to the critical damp and overdamp, you don't have such an MP. And the phase angle is starting from 0. This is very overdamped and coming goes to minus 180. Eventually this green one is overdamped system. Assign is the homework, and as I taught you, go and calculate this by hand. Okay. But in the first order system, guys, remember we didn't have such a overshoot MP maximum. We only had this. Okay, we only had this first order system. And the slope of this line is minus from here to here, almost minus 40 decibel. Minus 40 decibel over radian. Okay, here we go. Here is 40. Okay, Now, if I say, okay, you know what? Now I'm gonna connect this to the fourth order system. Fourth order system gonna be num of fourth order system gonna be, I don't know, say it is here is 1 0 0 0 0 1 S4 S actually 0 1, and then of fourth order system gonna be, I don't know, 1. What was the coefficients of the two spring and damper? Can you read for me? 1 1 17. How much was that? 1 1 17. Guys? Huh? Guys, can you hear me?
Yeah, it was
443. That's right. But when you're gonna find the open loop, you have to add the numerator denominator because this is open loop. So let me add it like this because you have to. This is open loop, but you have to add this to this for closed loop. Remember I told you? So your S score gonna be plus 1, gonna be 18, 5, and 13 plus 43. Look at here. You're gonna be 18, 5 plus 13. Gonna be 56. There we go. Now, if you wanna a fourth order system, let me put this here. I don't just. I'm gonna say figure 2. We don't need that. Okay, num 4 and dem 4. There we go. This is figure 1. Okay. Guys, see, the profile of the fourth order system shows you have an underdamped behavior, but it's a little different. This is because of the dominant pose I was talking about. See the phase portrait? See what I'm saying? It's kind of you have a kind of step here. See what I'm saying, everybody? Hmm? Yes, it's composed of 4 poles. One of them is very strong, 0.04, okay? And another is what? It's vanishing very fast. This vanishing very fast is gonna give you such a first order profile here, guys. Okay, you got it? So now you can put the 10th order, 20th order, and we're gonna talk about this later in the body designing controller for the frequency response, phase margin, and uh, and phase margin and gain margin. We're gonna talk about this later at the end of the semester. Okay. So we are done with these, and the next class I'm gonna go to the different kind of the error signals, and then the root stability criteria, and then we're gonna have midterm. Okay, you got it. Okay, so.